It's a beautiful thought. A single, elegant equation. Something you could write on a t-shirt. An equation that holds everything. The spin of a galaxy, the flicker of a candle, the firing of a neuron in your brain. The beginning of time and its ultimate end. The whole show described by one line of math. This is the dream. Physicists call it the theory of everything. Albert Einstein spent the last decades of his life chasing it. He failed. Many brilliant people since have taken up the hunt. They haven't found it yet. And the more we learn, the more we have to ask a difficult question: is this dream even possible? Or are we chasing a ghost? To understand the search, you have to understand the problem. The problem is that physics, as we know it, is split in two. We have two sets of rules for the universe, and they don't play well together. One set of rules is Einstein's general relativity. This is the theory of the big. It describes gravity. It tells us how planets orbit stars, how stars clump together into galaxies, and how the entire universe expands. It's a beautiful, sweeping theory. It says that space and time are not a fixed stage where things happen. They are a single fabric, space-time, and massive objects, like the sun, warp this fabric. Gravity isn't a mysterious force pulling the Earth. It's just the Earth following a straight line through the curved space around the sun. Think of a bowling ball on a trampoline. It makes a dip. If you roll a marble nearby, it circles the dip. That's gravity. General relativity works perfectly for big things. It's been tested again and again. It predicted black holes. It predicted gravitational waves. And we found them. It's a solid piece of work. The other set of rules is quantum mechanics. This is the theory of the small. It describes the world of atoms and the particles inside them. Electrons, photons, quarks. And this world is bizarre. It's nothing like our everyday world of bowling balls and marbles. In the quantum world, things don't have a definite location until you look at them. A particle can be in many places at once. It's a fuzzy cloud of probability. Things can pop in and out of existence. It's a world of chance and uncertainty, but for all its strangeness, quantum mechanics is also incredibly successful. It's the foundation for almost all modern technology: computers, lasers, nuclear energy, medical imaging. None of it would be possible without understanding the quantum world. So, we have two great theories. One for the big, one for the small. Both are right in their own domain. The problem comes when you need to describe something that is both very small and very massive. Where do these two worlds meet? There are two main places. One is the center of a black hole. An immense amount of mass crushed into an infinitely tiny point. A singularity. General relativity describes the immense mass. Quantum mechanics should describe the tiny point. When you try to put the equations together, they break. They spit out nonsense answers like infinities. The math falls apart. The other place is the very beginning of the universe. The Big Bang. The entire universe, all its matter and energy, was once packed into a point smaller than an atom. Incredibly hot, incredibly dense. To understand that moment, you need a theory that can handle both gravity and quantum mechanics. We don't have one. Our two pillars of modern physics can't talk to each other. They speak different languages. So, the search for a single equation, a theory of everything, is really a search for a unified theory of quantum gravity. A theory that can bridge this gap. A theory that can describe the universe at its most extreme moments. The most famous attempt is string theory. It's an idea that has been around for decades. And it's a very compelling one. The central idea is simple and elegant. If you zoom in on a fundamental particle like an electron, you won't see a point. Vibrating string of energy. That's it. Everything in the universe, all the different particles, are just different vibrations of these same fundamental strings. Think of a violin string. Plucking it one way gives you a C note. Plucking it another way gives you a G note. It's the same string, just different vibrations. String theory says the universe is like that. One kind of vibration shows up as an electron. Another shows up as a photon, the particle of light. Another vibration shows up as a quark. And here's the most beautiful part. One particular vibration pattern gives you a particle with the exact properties of the graviton. The graviton is the hypothetical quantum particle of gravity. In other words, gravity just naturally falls out of the theory. You don't have to force it in. It's already there as a specific note played on a universal string. This is a huge deal. It was the first time a theory managed to put gravity and quantum mechanics in the same mathematical framework. It seemed like the answer was within reach. But string theory comes with a lot of baggage. For one thing, the math doesn't work in our familiar 3 dimensions of space and 1 of time. It only works in 10 or 11 dimensions. So where are the other 6 or 7? The theory suggests they are curled up, incredibly tiny, at every point in space. So small, we can never perceive them. That's a wild idea, and it's very hard to prove or disprove. There's another, bigger problem. It turns out there isn't just one version of string theory. There are 5 of them, and then a later development called M theory seemed to unite those 5. But this M theory is so complex that no one knows its fundamental equations. And even within this framework, there isn't one single solution. There are what physicists call a landscape of possible solutions, something like 10 to the power of 500 possible universes, each with its own set of physical laws. That's a 1 followed by 500 zeros. It's a number so large, it's essentially meaningless. Our universe, with its specific laws, would be just one of these possibilities. If your theory allows for almost any kind of universe, it doesn't really explain why our universe is the way it is. It becomes less of a predictive theory and more of a landscape of possibilities. And crucially, string theory has not yet made a single testable prediction. It hasn't told us to look for a new particle or a new effect that we could then go and find in an experiment. Without a way to test it, to prove it wrong, some people argue it's not even science anymore. It's more like a philosophy or a mathematical exploration. That doesn't mean it's wrong. It just means it's stuck. There is another main contender, a rival idea. It's called loop quantum gravity. This theory takes a different approach. String theory starts with the particles and tries to explain gravity. Here, loop quantum gravity starts with space-time itself, the fabric of the universe that Einstein described. The core idea of loop quantum gravity is that space isn't a smooth, continuous sheet. If you could zoom in to the smallest possible scale, the Planck scale, you would see that space itself is made of tiny, discrete chunks. It's pixelated. Space is built from a network of interwoven finite loops. These loops connect to form a dynamic web. This is the fabric of space. Time, in this view, is not a continuous flow either. It's a series of discrete ticks, like the frames of a movie. One moment, one configuration of the network leads to the next. What we perceive as smooth, empty space is just the large-scale effect of this incredibly fine, granular structure. In this theory, gravity isn't a force carried by a particle. It's a direct feature of the geometry of this network. The way these loops are woven and connected defines the curvature of space. Loop quantum gravity is attractive because it's a more direct attempt to quantize gravity. It takes Einstein's idea that gravity is geometry and applies quantum rules to that geometry. It doesn't require extra dimensions, it doesn't require a whole zoo of new particles. But it has its own problems. Big ones. For one, it's been very difficult to show how the smooth space-time of Einstein's theory emerges from this weird, loopy quantum world at large scales. It's like knowing about individual water molecules but not being able to derive the properties of a wave in the ocean. The theory also struggles to incorporate the other forces of nature and all the known particles. It's a theory of quantum space, but it's not yet a theory of everything. So we have these two major paths, string theory and loop quantum gravity, and a few other less developed ideas. Both have brilliant people working on them. Both are mathematically deep, and both are a long way from being a final proven theory. This brings us to a bigger, more philosophical question. Let's say we find it. Let's say tomorrow a physicist writes down the equation. We test it. It works. It predicts everything we see. What would that equation actually tell us? It wouldn't be a simple thing like EMEC2. It would likely be an incredibly dense and complex mathematical object. It would need to contain all the information about the fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces. It would have to describe all the fundamental particles, the quarks, the leptons, the bosons. It would also have to explain the fundamental constants of nature. These constants are a deep mystery. Things like the speed of light, the strength of gravity, the charge of an electron. These are just numbers that we measure. They seem to be finely tuned. If the strength of the strong nuclear force were just a little bit different, stars couldn't form, and there would be no carbon, no life. If gravity were a little stronger, the universe would have collapsed back on itself long ago. If it were a little weaker, galaxies and stars would never have formed. Why do these constants have the specific values they do? Would a final equation explain them? Would it show that these values must be what they are for reasons of mathematical consistency? Or would the equation simply have to take them as inputs? Would it be a theory where we still have to plug in these measured numbers without knowing why they are what they are? If the equation could derive these constants from pure logic, it would be an incredible intellectual achievement. It would mean the structure of our universe is not arbitrary. It's a matter of mathematical necessity. But if the constants are just random, one possibility out of trillions in some string theory landscape, that feels less satisfying. It suggests our universe is just a cosmic accident. We just happen to live in one of the universes where the numbers were right for life to emerge. Then there are even deeper problems, problems that a physical equation might never be able to touch. Even a perfect theory of everything would describe the how of the universe. It would describe the machinery. It would tell us the rules the particles follow, but would it tell us why there is a universe at all? Why is there something rather than nothing? Why these rules and not some other rules? This is a question that may lie outside of science. It's a question of ultimate origins. An equation can describe the evolution of a system once it exists, but can it explain its own existence? And what about consciousness? What about the subjective experience of being you? The feeling of warmth from the sun, the redness of a rose, the sound of music. These are real phenomena. But they don't seem to be things that can be captured by an equation about particles and forces. You can describe the physics of the brain, the firing of neurons, the chemistry of neurotransmitters. You can describe the physics of light waves hitting a retina and sending signals to a visual cortex. But where in that description is the actual experience of seeing red? This is called the hard problem of consciousness. A theory of everything would be a theory of the universe's hardware. Consciousness, emotion, meaning, morality, meaning. These seem to be phenomena of a different kind. They are emergent properties, they arise from the complex interactions of the hardware, but they aren't reducible to it. A final equation could describe a brain, but it couldn't describe the mind. It could describe the world, but it couldn't describe our experience of the world. There's another, more mathematical reason to be skeptical. In the 1930s, a logician named Kurt Gödel came up with his incompleteness theorems. In simple terms, he proved that in any formal mathematical system that is complex enough to include basic arithmetic, there will always be true statements that cannot be proven within that system. The system will always be incomplete. You can add new axioms to prove those statements, but then new unprovable statements will appear. There is no finite set of axioms that can capture all of mathematical truth. What if the universe is like that? What if physics is like that? It could be that the universe is a system of such complexity that it cannot be fully described by any single finite set of equations. For any theory of everything we come up with, there might be phenomena in the universe that are true, that happen, but that cannot be derived from our theory. The universe itself might be logically inexhaustible. Our quest for a final, complete description might be doomed from the start. Not because we aren't clever enough, but because the very nature of reality is that it's always richer than any formal system we can invent to describe it. And let's not forget the elephant in the room, or rather, the dark elephant. All of our physics, general relativity, and quantum mechanics, all of it only describes about 5% of the universe. The rest is a complete mystery. About 27% of the universe seems to be made of something called dark matter. We can see its gravitational effects. It's what holds galaxies together. Without it, the stars on the outer edges would just fly off into space. We know it's there, but we have no idea what it is. It doesn't interact with light. It's invisible. The remaining 68% of the universe is even weirder. It's called dark energy. It seems to be a property of space itself, causing the expansion of the universe to accelerate. The universe is not just getting bigger, it's getting bigger faster. We have a name for this phenomenon, dark energy, but we have almost no clue what it is. It's one of the biggest mysteries in all of science. So, any theory of everything, any single equation would have to explain not just the 5% of the universe we understand, but the 95% we don't. It would have to tell us what dark matter is, it would have to tell us what dark energy is. Right now, our best candidate theories, like string theory, don't have clear, definitive answers for these massive questions. So, where does that leave us? The dream of a single, simple equation seems to be fading. The reality is that the universe is far more complex and far stranger than we imagined a century ago. It's possible that the search is misguided. Maybe there is no single equation. Maybe the universe operates on different principles at different scales, and there is no ultimate unifying master formula. Maybe the idea of a theory of everything is a product of our human desire for simplicity and finality, a desire the universe is under no obligation to satisfy. Or maybe we are just not there yet. Maybe we are like physicists in the 1890s who thought they had physics all figured out just before the twin revolutions of relativity and quantum mechanics blew everything wide open. We might be on the cusp of a completely new way of thinking about reality, something as profound as the shift from Newton to Einstein. The final theory might not look like an equation at all. It might be something else, a new kind of mathematical structure or a new principle we haven't even imagined yet. The quest for a theory of everything is one of the most ambitious and profound intellectual journeys humanity has ever embarked on. It has pushed the boundaries of our knowledge. It has forced us to confront the deepest questions about the nature of reality. But the path is not clear. The universe is not giving up its secrets easily. Perhaps the value is not in finding the final answer. Perhaps there is no final answer. Perhaps the value is in the search itself, the act of looking deeper, of asking harder questions, of constantly challenging our assumptions. It's a process that has revealed so much about the universe we live in. Even if a single equation for everything remains out of reach, the effort to find it will continue to teach us, to surprise us, and to deepen our sense of wonder. The universe is vast and old and complex. We are a small temporary part of it, trying to understand the whole. A single equation seems like a neat, tidy way to wrap it all up. But maybe the universe isn't neat and tidy. Maybe it's fundamentally messy, endlessly creative, and always more surprising than we expect. And maybe that's a more beautiful thought than any single equation could ever be. The search continues, and the mystery remains.